Thank you, Dr. Cherif, for the introduction. Good morning, everyone. My name is Abdelhakeem Badawy, and today, myself and my team here, Hoda Ahmed, Mohamed, Shahawy, Samah, Ayman, Samah, Hussein, and Yahya Abbas, will present to you ModReduce, which is a multi-knowledge distillation framework that supports online learning. So first things first, we will start with the project overview, and then we move to the hypotheses. Then the design, experimental setup, results, conclusions, empowerment outcome, and lastly, we have the future work. So let's start with the project overview. So basically, many of the real-life applications that we are using in our everyday life is based on deep neural networks. These include image recognition, speech recognition. Something is not okay. Medical diagnostics and smart assistants like Google Smart Assistant and Siri. So basically, our motivation here is to reduce the size of these deep neural networks. Why do we need to do this? Because deep neural networks are huge in size. They have billions of parameters at some times, and this large size places a challenge to embedded devices, to edge devices in general, like smartwatches, mobile phones, embedded systems, and autonomous cars, and many other applications. So our motivation here is to find a way to reduce these huge deep neural networks to a smaller one. So formally stated, our problem statement is as follows. Given a deep neural network with a large size, we aim at obtaining a smaller sized network, and this smaller sized network shall obtain a comparable accuracy and performance to the large network. So to do this, there are different ways for model reduction. These include knowledge distillation, pruning, and many other techniques. So we adopted the state-of-the-art method, or the state-of-the-art area in model reduction, which is knowledge distillation. And knowledge distillation, if I may give an analogy, is similar to an educational system in which we have an expert teacher that we assume has most of the knowledge, and this expert teacher is trying all the time to pass this knowledge to a student model or a student. So we have two main schemes here for this. The first scheme is having an offline scheme, and then this scheme, this is very similar to a teacher-student analogy. So the teacher has, we assume that the teacher has all the knowledge, and we are trying to extract as much of it as possible and pass it to the student. The other scheme is the online method, and this is a little bit different because here we do not assume that the teacher has all the knowledge. We assume that the teacher still can improve, and the teacher and the students are being trained synchronously and simultaneously. So what are the knowledge sources? We have three main knowledge sources. The first knowledge source is response-based knowledge source, and response is basically obtaining the response of the teacher and making the student trying to mimic this response. So for example, if we have a teacher that tries to predict the class of an image, so it predicts it's a cat with a probability like 0.9, and it predicts other predictions for the other classes, we try to make the student mimic this probability distribution. The second knowledge source is feature-based knowledge source, and by feature-based knowledge, we mean the knowledge that the teacher retains in its intermediate layers. So as you can see here in this shape, from layer M to layer N, these are the intermediate layers of the deep neural network, the teacher neural network. We are trying to figure out feature maps and pass them to the student model. Lastly, we have the relational-based knowledge, and in this we try to mimic the teacher's behavior when it places the different data instances in the space. So for example, a cat, two images of two different cats should be closer in the space than an image of a cat, for example, and a dog. So we try to make the student figure out this way of placing the different data instances in the space like the teacher. So now that we know what knowledge distillation is, we can move safely to the hypotheses.
Okay, so now that we know that knowledge distillation is a promising model compression technique, we aim to improve on it. But how can we achieve that? First of all, we have seen from our literature review and from the discussion Abdelhakeem provided that distilling knowledge from three types of that none of the current methods explore distilling 3 types of knowledge. They only explore distilling 1 or 2 types of knowledge. We claim that distilling 3 types of knowledge should yield better results than distilling only 1 or 2 of those knowledge types. Furthermore, we claim that combining two knowledge distillation strategies like offline and online learning in a unified framework should enhance the performance of our novel framework, ModReduce. Now we move on to the discussion of the specifics of our novel framework with Samah.
Okay, so I'll go through our design for you. First, I'll go through the system specifications. Next, I'll discuss the architectural design. And finally, I'll explain to you our development phases. So for our system specifications and features, so our framework aims to have these following offline learning techniques ingrained into it. For response knowledge distillation, we aim to have the Hinton knowledge distillation, which is the state of the art and the pioneer in response knowledge distillation and knowledge distillation as a whole. For feature knowledge distillation, we aim to have Fitness, which is the pioneer in feature knowledge distillation, and SimCity, which is the current state of the art in feature knowledge distillation. And finally, for relational knowledge distillation, we aim to have RKD and CRD, which is the state of the art in relational knowledge distillation. Next, for the online learning implementations that we aim to have in our framework, we have PCL, which is peer collaborative learning, where different students learn from each other, and FC, which is fully connected ensembling, where the students learn the ensemble weights from each other. And finally, N1, which is on the fly native ensembling, and weighted averaging, where there is a learned weight for each student based on their performance in the previous epochs, and this is used to provide a group output. Next, so for our feature framework, so we have a unified framework for different knowledge distillation techniques, in which we learn from different types of knowledge, the 3 different types of knowledge response, feature, and the relational. And we employ online learning, and we provide a better performance than state-of-the-art knowledge distillation techniques. So for our architectural design, as you can see here, this is the architectural design of our framework. We aim to have 1 expert teacher model and 3 smaller naive student models. Our training is divided into 2 phases. The first phase is the offline learning, in which we distill a different kind of knowledge into each student. So 1 student is learning response-based, the second is feature-based, and the third is relational-based. And the second phase is online learning, in which the 3 smaller students learn from each other. Now for the development phases and major milestones in our project. For phase 1, so we aim to have the basic skeleton of our framework and architecture implemented. So we implemented the most simplistic knowledge distillation techniques in each aspect, which is Hinton, Fitness, and RKD. And for online learning, we use naive aggregation. We exited this phase having proved our concept. So our framework did perform better than the basic offline knowledge distillation techniques on their own. So we had the proof of concept for our hypothesis. Next, for phase 2. Instead of the basic architectures, now we have the state-of-the-art architectures implemented, which are SimCity and CRD. And Hinton is still implemented, as you can see, because it is the state-of-the-art in response knowledge distillation until now. Out of this phase, we had implemented the state-of-the-art offline techniques, and we had verified our design with different knowledge distillation techniques. Next, for phase 3 and then our final phase, we had implemented the 4 knowledge distillation types, as you can see here. Now our framework, we could perform training using different combinations of online techniques and offline techniques, and we could do all the experiments that we had targeted in the first place. Now, at the end of this development plan, our framework was very modular. It was extremely customizable, where we could use any number of students, any network architecture, or any combination of offline and online implementations. And it supports a very wide range of techniques. And it was actually really pluggable, where you could easily add another offline technique or online technique and use it as well. Next, we'll go through the experimental setup with Samah.
So in this phase, we're going to go through the entire flow chart of our experimentation setup, which explains our rationale behind what we have designed in our experiments. So at the beginning, we started with the essential question of our hypothesis, where does distilling knowledge from 3 sources produce better results than distilling only one knowledge source or not? So if the answer to this question was yes, the next please. If the answer was yes, that means that our hypothesis was originally verified, that only the offline aggregation of the 3 knowledge sources produces already better results. And at this point, we wouldn't need any further experimentation. But if the answer was no, then that means we have to alter our aggregation method itself, and we have to try the online learning instead of the offline learning technique. And at this point, we found the answer to be no. So we tried the different, to go for the direction of the online learning. So the question now becomes, does online learning of the online learning technique aggregation of the 3 knowledge sources produces better results or not? So if the answer was no, then this falsifies our original hypothesis, and now we have no direction to go. But if the answer was yes, then now we talk. That means that online learning technique provides better results than distilling only one knowledge source. And at this point of time, we found the answer to be yes. So the question now becomes, which specific online learning technique produces better results? And we have tried 4 different online learning techniques, as you can see here. This is the peer collaborative learning, BCL, and the fully connected layers, FC, on the Fly Native Ensemble 1, and the weighted averaging. And finally, we found that weighted averaging was the best performing online technique to distill the knowledge from the 3 different knowledge sources in each student and aggregating them to get the final group output. So in order to perform these experiments, and we had the following setup. We had this data set, which is C400. The C400 consists of 100 classes, where we have 600 images per class. Those 600 images are 500 images for training and 100 images for testing. And for the benchmarks that we compared our results against, we have here 3 different benchmarks shown here. The Hampton benchmark for response-based knowledge, the SimCKD benchmark, which is for the feature-based knowledge, and CRD benchmark, which is the relational-based knowledge distillation. And in the following here, we have created a novel benchmark. This novel benchmark combines both experiments performed in both state-of-the-art techniques in SimCKD and in CRD. And in addition, it has all its setup. We have replicated those experiments so that we can compare our results not only to one benchmark, but to those all available benchmarks. And here we can have an overview of what we have created in this benchmark. What we can see here is a summary of the 15 different experiments reported in SimCKD and CRD as well, and we should know that these are MIT-produced papers as well. Here we have, in the same benchmark, we are reporting the accuracies by the original expert-teacher model, the base student model, Hampton accuracy, SimCKD accuracy, CRD accuracy, and our own accuracies, mod-reduced accuracies. These are the last row. And the bolded values are the most or the best results that performed in each experiment. So now we will go through the detailed results of our experiments with Mahfouz.
Okay, so we have now seen the general setup of the experiments. We have 15 experiments, and these experiments basically merged the state-of-the-art experiments. Out of these 15 experiments, we actually surpassed the state-of-the-art in 10 experiments. And let me walk you through the detailed results. First of all, our evaluation metric. And for evaluation metric, we're using a metric called average relative improvement, which was actually introduced by CRD in their paper and was used by SimCKD after them in order to compare to other knowledge distillation techniques. And simply the relative improvement is, if you have like our model is called mod reduce. So you see the improvement of our model on a specific knowledge distillation technique and divide this value by the knowledge distillation technique improvement upon the naive student model, the simplest model out there. And then you calculate the average for all the 15 experiments, and that should be a good metric to represent how your framework is performing against the current state of the art. Now, moving on to the results. we have discussed that we've implemented 4 online learning techniques into our framework, PCL, 1, FC, and weighted averaging. And now let's go deep into the ARI, or the average relative improvement result per each model, starting with PCL. So for PCL, you can see that over the Hinton model, which is the response-based knowledge, we have actually improved by 11.89%. However, in case of the feature and the relational knowledge, we have degraded the model by -10%, -12%. So PCL is not that good. So we move on to the next online learning technique, which is 1. And we can see here that all the numbers are positive, which means that our model actually improved on Hinton, SimCKD, and CRD, which are all the state of the art in their field. Moving on to the next online aggregation method, which is FC. And we can see here that also we have an improvement over Hinton and SimCKD, which are actually part of our structure. But however, we are lacking by about -0.35% in CRD. Now, moving on to our last online technique, experimentation, which is weighted averaging, which is actually the most promising and the one that we have chosen to progress with and present. Thank you. So now moving on to our most promising results of aggregation, online aggregation method, which is weighted averaging. And in weighted averaging, we can see that we are actually surpassing the state of the art with their metric, which is ARI, in all of the knowledge techniques. So we are improving upon Hinton by 48%, improving upon SimCKD by 25.5%, and improving upon CRD by 17.46%. Now let's examine the next slide, which, next slide, please. Okay, so this tells us the difference between offline aggregation, simply adding the offline knowledges from the different sources. And we can see it's not performing well on average, actually performing worse than the state of the art. However, when we aggregate the knowledge through online methods, through weighted averaging, to be specific here, we can see that we are improving upon the state of the art. Now we will move on and explain more detailed results on our experimentation for weighted averaging. You can see here we speak colors, okay? So first of all, the yellow color is simply the teacher accuracy, which should always be greater because the teacher model is a huge model that can take a lot of data. Then the student accuracy, which is like the naive student that we train directly using the normal training methods. And then next we have the orange, light blue, and the red and the green. These are the knowledge distillation schemes. Our model is simply mod reduced with weighted averaging, the green one. In the next experiments, if the green one surpasses the other colors, it means that actually our model is performing better than the state of the art. So moving on to the results, these are like a set of 6 experiments. And in these experiments, you can see out of the 6 experiments, 3 of them were actually surpassing all of the state of the art. And interestingly, if we look at experiment number 5, our naive student model used to perform at 71.14% is exceeding the expert model at 74.31% when we use our knowledge distillation schemes, which means the student has actually surpassed not only the offline knowledge distillation, but also the teacher model. Moving on to the next set of experiments, and at these 6 experiments, we are at 5 of them, we're surpassing all of the state of the art. And again, we can see here that we are actually doing very equivalent to the teacher accuracy. The last 3 experiments, and out of those 3, again, we are doing better in 2 experiments. So what about the bad results? So let's take 2 bad results out of their context and look at them. Are we actually doing worse than everyone in the bad results? Actually, no. If we look here, CRD is the state of the art in relational knowledge distillation, which is the red one, and the light blue is the state of the art in feature. And our model is doing between them. So even when we are doing bad, we're not doing that bad. We are, on average, we are doing actually really good compared even to the state of the art. So we move on to sum up all the results. So with the metric that is used in the state of the art, the ARI, over Hinton, we are producing on average an improvement of 48.29%. The worst improvement is 2.35%, while the best improvement is 135%. And for SimCKD, which is the state of the art in feature knowledge distillation, on average, we are improving in the 15 experiments by 25.5%. The worst degradation is simply minus 9.22%. However, our best relative improvement is 153%. For CRD, which is the state of the art, again, relational knowledge distillation, on average, in all the 15 experiments, we're improving by 17.64%. Our worst degradation is minus 23.78%. However, our best relative improvement is 62.28%, which is simply, these results clearly shows that our moderate use framework combines the best of all offline knowledge distillation worlds. And now we move on to the conclusions with Yahya.
Okay, thank you, Mohamed. So now let's discuss our conclusions after such a detailed results from Mohamed. Let's first look at our work summary. First of all, we have seen through our discussion that we have constructed a comprehensive benchmark that combines 15 experiments reported in both state-of-the-art knowledge distillation methods we compare ourselves against. We have also incorporated 4 different online learning techniques, which led to us having about more than 225 experiments. This led also to about 2,860 training hours. And now let's move on to summing our findings. The first finding we have is that weighted averaging is the best online learning method from the results we had. And overall, in the 15 experiments, we surpassed both SIMSCD and CRD in 10 out of the 15 experiments. Now let's look at detailed results compared to SIMSCD and CRD alone. We surpassed SIMSCD, which is the state of the art in feature knowledge distillation, in 6 out of the 7 experiments they have reported in their paper. As for CRD, we have surpassed or outperformed them in 7 out of the 11 experiments they report. So what can we conclude from that? We have 2 conclusions. First is that using online learning as an aggregation method for different knowledge sources is better than simply combining the losses in a single student. The second conclusion is that distilling 3 types of knowledge into a student leads to better results than only using 1 or 2 knowledge distillation types. And now we move on to the empowerment outcome with
And for our empowerment outcome, our main empowerment outcome is research oriented, meaning that we are producing a publication of this project, and in this research we provided a proof that our newly introduced framework enhances the distillation performance compared to state-of-the-art methods when having the same parameters, hyperparameter configuration, reduction ratios, and teacher-student combination. And our results in a scientific methodology and with comparable benchmarks. In this, our results support our hypothesis, and that they clearly demonstrate that the performance of our benchmarks is better than the performance of the other benchmarks reported by the other benchmarks. And this is the draft of our paper. And for the future work, we will attempt to test the distal of the effect of the distal of 2 knowledge sources instead of 3. And we attempting to change the number of student models, and monitoring the effect of this change. And we will look into the result of switching 2 different training schemes, one of which is synchronized between online and offline learning, and the other is sequential. And we will look into the result of experimenting with using different student architecture for different knowledge sources and monitoring the effect of this change. And we will conduct an ablation study to see how the different components of the system will affect or influence for our system.
and we will experimenting using using the new teacher student combination to expand the weights of the present benchmarks. And thank you for our supervisors. Thank you for all.